All right, hello everyone, and welcome back to these astronomy talks. So last week we looked at the different types of galaxies, and we started to get a taste for cosmology. We saw how we have the cosmic distance ladder, how we use different distance measurements to get distances to very, very far away galaxies, and we also got a taste of the fact that the universe is expanding. That expansion rate tells us the universe's age of about 14 billion years. So tonight, we will now look at how galaxies form and evolve through our universe in this topic of galaxy evolution. Now, I have to say, this is the stuff that I study as a semi-professional astronomer, as a budding new astronomer. With that knowledge, I can tell you that everything we're talking about tonight has a lot of unanswered questions, and you can get very complex. We're going to try and do just a very surface level of galaxy evolution. But I just want to stress that everything we're about to talk about tonight is still very much new and at the forefront of what modern astronomers are researching, at least galactic astronomers are doing. So without further ado, here's tonight's quote. Scientists normally like to do experiments. You know, they like to mix this with that and see what happens. They like to take this thing and poke it and see how it reacts. In astronomy, we can't do that. The stars, the planets, the galaxies are so far away that we just look at them, and we have to learn things by looking at them. So speaking of looking at things, let's just quickly refresh one of the topics that we ended with last time, the look back time. So remember, any evidence of galactic evolution that we have is just based on a snapshot, just one brief instance of a galaxy's lifetime, because galaxies evolve on timescales much longer than human civilization even. They take millions and billions of years to change and morph and evolve. And so, yeah, we're stuck with just a picture of one galaxy, a picture of another, and we have to just kind of infer what is happening in between these two pictures. Those most distant galaxies that we can see had stars in place more than 13 billion years ago. So when the universe was very, very, very young. Now, conveniently, that's also about the same age as the oldest stars in our galaxy. So that tells us that it's safe to assume that most galaxies formed at about this time, about 13, 14 billion years ago. And so a galaxy's look-back time will then be directly linked to its age. So for example, a galaxy with a look-back time of 13 billion years, gigayears, in a 14 billion year old universe must be a billion years old. And just keep that in your head as we talk about galaxies that are these incredibly far distances. We're also talking about how old they are, what stage of their evolution they are in. And so this, by photographing galaxies at different distances, essentially we can get sort of a scrapbook of a galaxy's life, hopefully, if all galaxies evolve the same way. So pictures of the most distant galaxies show galaxies in their childhood, and pictures of galaxies nearby show them as they are today. And we've seen a lot of that last week. For example, here is the Hubble Legacy Field, not the Hubble Ultra Deep Field, but the Hubble Legacy Field. And let's just focus on this particular square here and zoom in. And we can see galaxies in many different types. There's sort of this little chain happening here. But each of these galaxies, and indeed, not just, these big bright galaxies here, but at all little points in the background, those are all different galaxies at different stages of their life. And so we're able to look back across time. So for example, here is some of those galaxies in the Hubble Legacy Field. You can see very recently, within the last within a half a billion light years away, all the way to when the universe was very young at the bottom row, between 12 and 13 billion light years away. each of these individual photographs shows a single galaxy at a single stage in its life, and measuring the redshift of that galaxy will allow us to place it on a timeline of the universe. And so we can see how galaxies of a particular type have evolved. Now, this is sadly about as far back as we can go with current technologies. We've got to really wait on the launch of the James Webb Space Telescope, ideally on Halloween this year, October 31st of 2021. We're crossing our fingers. See here in this tongue-in-cheek plot from XKCD, James Webb at one point was going to launch in like the late 2000s. It is now 2021. It's looking like it's going to be launching on Halloween this year. However, this comes with a caveat. We have said that many times before. So we're hoping, as XKCD points out, at least the slope is less than 1. If anything, it's gonna have to launch by 2026 according to this trend line. So without the data from the James Webb Space Telescope, which can see even further into the past than the Hubble Space Telescope, we'll have to rely on some theoretical models. And those models all start with the same 2 key assumptions. First one is that hydrogen and helium gas, along with a lot of dark matter, filled all of space almost uniformly in the first few million years of the universe. Almost, that's the key word there because it goes into the second assumption. However, the distribution was not perfectly uniform, which left some regions more dense than others, and those denser regions served as seeds for galaxy formation. And so beginning from these assumptions, we can use the laws of physics and computer simulations to show how galaxies, how we think they formed and evolved. And those models show that the slightly greater pull of gravity around the enhanced density seeds would have halted the expansion of these regions within about 1 billion years, even as the universe as a whole continued to expand. And the material in these regions then contracted into protogalactic clouds, much like the stuff that formed the Milky Way. So let's take our mind back about 2 weeks and remember that kind of monolithic model, that protogalactic gas cloud model for forming the Milky Way. So we've talked about all this before. So we've got just this huge cloud of hydrogen and helium with some embedded in some dark matter. And early on, gravity would have drawn in matter from all directions, creating this sort of blobby cloud that would start to fragment, just like molecular clouds fragment as they're forming stars. This protogalactic cloud would fragment and form stars, and those early stars would have orbits with any orientation, forming globular clusters, forming halo stars. But as time passed, as gravity continued to contract the cloud, we know that the law of conservation of angular momentum would have started everything to really spinning. And instead of continuing to contract into a spherical blob, it would have smoothed out into a disk, into a spinning disk, all going the same direction. And stars would form from that disk. And so we have all the disk stars that are in the Milky Way's disk, as well as the disks of all the other spiral galaxies. And those would have very orderly orbits. Now remember, this explains, this model explains the ages and metallicities of the halo and the disk stars, those different ages and metallicities, where the halo stars are older and don't have as many metals. The disk stars are much younger and have a wide variety of metals in them, but it didn't explain everything. Still, this is a good base model for how spirals exist, how spiral galaxies exist. However, this model, in terms of trying to explain all galaxy evolution, not just the Milky Way, not just spirals, leaves 2 questions unanswered. The first one is, this model assumes that galaxies formed in regions of slightly enhanced density, where there just happen to be more hydrogen, helium, and dark matter there. But it doesn't tell us where those density enhancements came from. And it doesn't while this basic model does do a great job of explaining how spiral galaxies might form, it doesn't really explain why some galaxies are elliptical and some are irregular. That is left unanswered in this model. That first question, that is a question of cosmology, and we will talk about that, start to talk about that next week and the week after. So let's focus on that bottom question. What about ellipticals and irregulars? So there's that big difference between those three different types of galaxies. Spirals have those beautiful spiral arms and a flat disk. Ellipticals are just kind of bulgy and old. Irregulars are any shape they want. And our job as galactic astronomers is we want to be able to tell the story of each different type and each individual galaxy, ideally, just as we can tell you the entire life of a star based on its mass. But as I keep saying, many of this is subject to ongoing and very active research. So what we're just going to talk about here is very general outlines of theories that are still being worked on. They're still being figured out. So one of the two ways that galaxies can differ is maybe in their birth conditions. Either maybe elliptical galaxies end up looking different from spirals because of birth conditions, or their beginnings are similar to spiral galaxies, but later on they become different due to interactions with other galaxies. Let's focus on the birth conditions first. So there are two different types of birth conditions that maybe could create the difference that we see between ellipticals and spirals. So the first one is protogalactic rotation. Basically, if that original gas cloud had a lot of angular momentum, it was really rotating around an axis already, then it would have continued to increase that rotation as it collapsed, which would then form a disk and thus a spiral galaxy. Otherwise, as it just kind of gradually collapsing on itself, it would have stayed relatively spherical and formed an elliptical galaxy. You see an image, you see diagrams of that at the top. The other way you could get an elliptical and a spiral is maybe by changing the density of that protogalactic gas cloud. If the original gas cloud was very dense, then stars would form much more rapidly before the entire cloud had the chance to settle into a disk, thus leaving behind an elliptical. Otherwise, if it wasn't that dense of a gas cloud, then we would be able to, those stars would form much more slowly, allowing the whole gas cloud to collapse into a disk, and we would get a spiral. Evidence for this kind of role of birth conditions, whether it's the rotation or the density, comes from a few giant elliptical galaxies at very great distances. So these galaxies lack those blue and white stars, indicating that there are no new stars are forming within them, even though we are seeing them as they were when the universe was very young. So that suggests that all the stars in these elliptical galaxies were born almost the same time, which is consistent with the idea that all the stars form before a disk could develop. So for example, here's that very famous Hubble Ultra Deep Field, and we're zooming in on this little square down here. We're not really paying attention to this big spiral, but if we look at in the infrared, we see this kind of red dot above the big spiral. And zooming in, that real red dot is an elliptical galaxy, a very, very young elliptical galaxy, and is very, very red. Telling you once again that there are none of those blue, white, young stars, meaning that this elliptical's already formed all of those, and they've all died out already, leaving behind just the old red stars, and it's not undergoing any sort of star formation here. So that is one of those evidence for birth conditions being a prominent role in the difference between spirals and ellipticals. But birth differences can't account for all the differences we see among spirals, ellipticals, and irregulars, because the birth conditions ignore one very key fact, and that is that galaxies don't just sit out there and evolve in isolation. They are often in very active groups and clusters. And so birth conditions can't play the entire role. So for example, if you remember all the way back on our very first talk, we put the solar system into perspective by imagining the sun as a grapefruit, placing it at the center ring in Centennial Olympic Park in Atlanta, Georgia, and then putting the planets to scale. Now remember, to get to Neptune, to get to Pluto, Neptune was fitting in the Georgia Aquarium, a long way away from the sun. Here, now I've made the Milky Way a grapefruit. And let's put other galaxies around it. So you see the blue dot at the center of the middle ring is the Milky Way. We've got the large and small Magellanic Clouds here. We've got Andromeda and the Triangulum Galaxy. That's the entire local group. There's a smattering of smaller galaxies, but most of it can fit in just within the middle ring. We're talking trillions of stars here. A handful of galaxies can fit within the middle ring. Meanwhile, Neptune was in the Georgia Aquarium. Now, on the right are some even more distant galaxies, and we still haven't even really made it outside the fountain area for the nearest galaxies. So galaxies are much on this scale, on this sort of grapefruit size scale, they're much more compact, much more close together than the planets are in the solar system on the same scale. So, so simply put, galaxies do not evolve in isolation. They are with tons and tons of neighbors and friends. So that means that galaxy collisions are inevitable. They do happen. And of course, our Milky Way is not immune. We are currently cannibalizing the Sagittarius dwarf spheroidal galaxy at the moment. It is currently crashing through the other side of the Milky Way's disk. Now, that's not as dramatic as some of the more beautiful collisions. Here's just a handful of them. Going from Mayall's object up at the top left, where we see a galaxy physically crashing through the disk of another. We've got ARC 238, where these two galaxies are kind of doing a ballet dance, tossing out these tidal tails and maybe a bridge between them. We have the Tadpole Galaxy, where we've already got two galaxies that are in the final stages of their merger, but we can still see the tails and curls from the merger. We've got ARC 157, where we can clearly sort of see that X shape of those two galaxies violently crashing into each other. AGC 7714, another one that's going through some tails. And indeed, the background image for these slides is another galaxy merger, the Mice galaxies. All of these we see as snapshots all over the night sky. And we think collisions might have been even more frequent in the distant past, when the universe was smaller and galaxies were closer together. And indeed, high redshift observations show many distorted-looking galaxies. Not many fully formed spirals and ellipticals. So here is a bunch of galaxies. The ages here tell us how young the universe was when these galaxies were formed. So, for example, this spiral up here, the universe was already 8 billion years old by the time this spiral existed. So you can see that there are tons of clumpy things, what people are calling tadpoles, maybe an elliptical, but even though that's relatively late in the universe's age, some chains, mergers, bent chains, rings even. There's not many typically looking spirals and ellipticals in the early universe. It's all a bunch of kind of blobs. And so we can get a good idea of what mergers are doing by taking these snapshots. However, we can learn a lot more with the aid of computer simulations that allow us to watch these collisions that in nature take hundreds of millions of years to unfold. And these simulations show that a collision between two spiral galaxies can create an elliptical galaxy. Those tremendous tidal forces between the colliding galaxies tear apart the two disks, randomizing the orbits of those stars. And meanwhile, a large fraction of their gas sinks to the center of the collision and rapidly forms new stars. Supernovae and stellar winds will eventually blow away the rest of the gas. And when that cataclysm finally settles down, the merger of the two spirals has produced a singular elliptical galaxy. And so it has little gas left for a disk, and the orbits of the stars have random orientations. Here's I'm going to show you a beautiful animation of two spirals merging together. And the animation will stop a few moments, rotate itself, and show you an actual picture that they're trying to replicate. So let's watch this animation to get a sense for these huge galactic mergers. So we've got our two spirals. We're going to come in and look. That looks like that group of galaxies. And there we have Mayal's object. We're going to toss out these nice tidal tails. Get something that looks like that. And they're going to rebound back into each other to go for a second pass. It's a beautiful, beautiful simulation there. Once again, by my advisor here at Case Western. So we've got these models, we've got these simulations, we're gonna look at snapshots, but what's the evidence? So there's plenty of observations that do support the idea that some elliptical galaxies do result from the collisions of spirals, because elliptical galaxies dominate the cores of galaxy clusters, where collisions should be the most frequent, just because of the density of galaxies. You see here, this galaxy cluster Abell 1689. And if you look towards the center of the image, you see a lot of just kind of round, blobby looking galaxies. Yellowish, they're not, if you look at the outskirts, you see all these nice blue-white spirals. All these are yellowish, dead. They're not doing any star formation. They're kind of blobby. Those are elliptical galaxies. You can see some smears like this one, gravitational lensing as well. These are ellipticals and lenticular galaxies. Stronger evidence comes from the structural details of elliptical galaxies. So for example, NGC 474 down here has stars and gas clouds in orbit, suggesting that they're leftover pieces of galaxies. So here you can see, although this galaxy is not a member of a cluster, it has some unusual structures, these kind of shells here. That's probably the result of a collision. The shells on this surrounding this galaxy are made of stars on orbits that are hard to explain, yet the entire galaxy came from a single protogalactic gas cloud collapsing. The stars that we see in the shells are probably plunged back and forth through the central part of the galaxy, each swinging from one side to the other like a pendulum. And those shells represent the extreme ends of these plunging orbits where the stars spend most of their lifetime. However, the most decisive evidence for the evolution of elliptic galaxies comes from these central dominant galaxies at the heart of many dense clusters. Here is another galaxy cluster, Abell 3827. And this whole kind of fuzzy yellow area, that is the galaxy. And these four kind of blobs here, those are the cores of galaxies this one has swallowed. These centrally dominant galaxies often have tons of evidence, tons of clumps of stars that are the remains of galactic cannibalism of these unfortunate galaxies that simply just passed too close and got swallowed up. The elliptical here in this image has a mass of around 30 times that of the Milky Way. These can make them some of the most massive galaxies in the universe. So galactic cannibalism can turn spirals into ellipticals. Another mechanism that can turn spirals into ellipticals is gas removal. The technical name for this is called ram pressure stripping. So, for example, when a spiral, let me back up, all galaxy clusters contain a lot of really hot gas, really hot ionized gas. And so when a spiral, say from the outside of the cluster, comes in its normal orbit, coming in towards the center, it will pass through all this hot gas. And that hot cluster gas will exert a drag force, will exert some friction on the galaxy's gas, leaving the stars alone, but actually removing the gas, leaving it behind. And so without any gas in the galaxy, it can't form any new stars. And so it'll gradually, all the young stars will die out, leaving behind just a bunch of old red and dead stars, giving you a lenticular or an elliptical galaxy. Here is the Perseus cluster shown in visible X-ray, radio, and infrared light. And you can see, yes, all the galaxies of the cluster, but you see all the purple and blue, all the purple and red gas, that is the hot ionized gas of the cluster. Here is one galaxy that is, we think, undergoing this ram pressure stripping, NGC 4402. You can see where the stars are. That is the straight line of white here. And then you can see the dust, it kind of forms a sort of bowl shape. We think it's going through ram pressure stripping as it moves through the Virgo cluster. Eventually, it will also become red and dead, making it look like a lenticular or an elliptical galaxy. So we've now seen, some differing birth conditions can create spirals and ellipticals. Later on, interactions through these galaxy mergers, we can turn spirals into ellipticals. And so the overall answer is probably a mixture of these two ideas. Birth conditions may explain why most galaxies are either spiral or elliptical, while interactions may explain why ellipticals are common in clusters and spirals are common elsewhere in the field, as we would say. And so the general consensus is that galaxies must begin as these active star-forming systems that can later grow larger as they collide and merge with other galaxies, and that some galaxies eventually exhaust their supply of cold gas for star formation. This sequence of events actually accounts for the division between the red sequence and the blue cloud on a galaxy's HR diagram, which we first saw last time. So all galaxies will begin as members of the blue cloud during their initial period of star formation, because active star formation makes them blue-white in color. Some of them will grow larger through collisions and mergers, ultimately becoming large elliptical galaxies, so moving up here as they grow in mass. Their young stars die out and they'll move up into the red sequence. These large elliptical galaxies are red because their star formation has ceased. Meanwhile, star formation can also cease in smaller galaxies that have used up their supply of cool gas, causing those galaxies to become the smaller members of the red sequence. However, we definitely need more observations to fully test this idea. So so we've sort of explained, hopefully, we've given you a hint of how galaxies form. It's a combination of birth conditions and later interactions. Now let's talk about the stuff that happens to them after they form. And our discussions here have assumed that kind of star-gas-star cycle, which we talked about in greater detail with the Milky Way. Go back and watch that lecture if you need a refresher. We're assuming this kind of star-gas-star cycle happens at a fairly steady rate in spirals, while ellipticals consist of just stars that are formed in the distant past. However, observations show that star formation rate can vary dramatically throughout a galaxy's lifetime, depending on the amount of cold gas available for star formation at any given time. In particular, a small percentage of galaxies are starburst galaxies, not named after the candy, although it's a great name, where these starburst galaxies are undergoing a rapid burst of star formation. So for example, the Milky Way forms about one star per year. pretty standard. While starburst galaxies can form hundreds of stars per year, many times the star formation rate of the Milky Way. And this actually kind of poses a problem for starburst galaxies, because if a starburst galaxy just was going constantly at hundreds of stars per year, it would use up all of its gas in a few 100 million years. But galaxies are billions of years old. So this phase, this kind of starburst phase, must be a very short phase in a galaxy's life. After its starburst is over, presumably it will just return to being an ordinary spiral, elliptical, or irregular galaxy. A great example of a starburst is NGC 1569 here. I studied it for a little while in undergrad. It's a really booming galaxies. And what really helps us recognize how impressively fast these galaxies are forming stars is by looking at them in the infrared. The reason is, sorry, excuse me. The reason we can understand by looking at the infrared is, remember, dust absorbs blue light. It lets red light kind of pass through it, mostly unchanged. And because these are going through tons of bursts of star formation, there's going to be a lot of molecular clouds that are going to conceal the younger stars. So by looking at the infrared, we can actually see the clouds themselves and the stars again. And these, looking at the infrared allows us to see way more light than we can see in the visible thanks to that dust. So the infrared output is usually around 1 trillion times that of our sun. Compare that to the visible output of around 10 billion times the luminosity of our sun. So looking at infrared actually makes them appear 100 times brighter in infrared light than in visible light. We call these things ultra-luminous infrared galaxies, or ULIRGs. They're also extreme, and there's hyper. We're very good at names, astronomers. So these are very big, bright, booming galaxies. But a star formation rate of 100 times the Milky Way's also means that supernovae will occur at 100 times the Milky Way's rate. And just like we talked about with the Milky Way, each of those supernovae are going to create a bubble, which will overlap with neighboring bubbles to form a superbubble. And then more will happen inside the superbubble. More supernovae will happen inside the superbubble, which will add to the superbubble's energy. Eventually, the result is a huge galactic wind. Low density gas, but extremely hot, around 10 to 100 million Kelvin. That will expand beyond the galaxy, causing star formation to shut off for billions of years. So essentially the galaxy is this weird feedback loop where the galaxy goes through this huge burst of star formation, but then blows out all the gas it can use to continue all that star formation. Maybe resuming again if the gas that has been blown outside the galaxy cools off and falls back on to the galaxy. So here's a very good example of a huge galactic wind in the Cigar galaxy, Messier 82. Up at the top left, you can see it in the visible. Here's the disk, and here is all this ionized gas, this H alpha coming off of the disk. If we look at it in a combination visible, infrared, and X-ray light, you can see even more of that gas being blown away from the disk. So over the next millions of years, the Cigar galaxy will shut off. It will stop forming stars because it's blown out all of its gas. And so clearly the star formation rate is not a constant function and can actually vary quite dramatically over time. So that means we've got to correct this star-gas-star cycle, since galactic evolution depends on the gas both inside and outside of the galaxy. This is a beautiful illustration of the entire process used in a paper talking about the circumgalactic medium, the gas that is between galaxies. Where it might be blowing some gas out as outflows. Maybe that will eventually cool and fall right back on as recycled gas. Maybe a galaxy is accreting gas, new gas from the surrounding intergalactic medium. And there's just diffuse gas that maybe can pass through as it moves throughout the universe. You see the year on this, 2017. This is something we've only recently really begun thinking about. in much greater detail how important this is. So clearly it's not just the gas inside the galaxy that matters, but it's the gas that's inside and around the galaxy that matters. Now, sometimes I want to talk about these sort of active galaxies. Sometimes galaxies can do really weird things. So let's take a bit of a history lesson here. So back in 1917, Heber Curtis, and that, yes, the same Heber Curtis that was in the Great Debates that we talked about a week ago, he noticed that there's this curious straight ray emanating from the center of the elliptical Messier 87 in Virgo. You see my arrow pointing to this weird little ray from Messier 87. He had no idea what to make of it, and no one else did, so we moved on. Then in the 1940s, 30 years later, Carl Seifert noticed that some spiral galaxies have these very bright, almost point-like, almost star-like bulges. For example, here is AGC 5548, where you can see the disk, but wow, is that bulge is so bright, it's actually causing a diffraction pattern from the camera. It's actually overwhelming the camera and causing it to appear like a star. We took the spectrum of galaxies like this one, and they came in two types. They had either broad spectra or narrow spectra, type 1 or type 2. So here you can see on top an example of broad spectra, where instead of these narrow peaks like we see at the bottom, where it's just kind of a straight line up, you've got this kind of build up. It looks way more like a mountain, where it's kind of got a fat base and a narrow top. It's a broad line spectrum. All right, so we kind of like, well, that's weird. And we just kind of put it off to the side. We don't know what to make of those either. Then in the 1950s, when we started doing radio surveys of the sky, we started to identify these really bright radio sources, often with no optical counterpart. So here is 3C273. The 3C stands for the third Cambridge Catalog of Radio Sources, and it's the 273rd entry in that catalog. It's also in Virgo. 3C273 is right here at the center. And look, we've got another curious straight ray. It's weird. These objects were dubbed quasars, quasi-stellar radio sources, because these were star-like in appearance. I mean, I don't see a galaxy disk around this thing. It just looks like a really big star. But the problem is stars don't emit strongly in the radio. So we had no idea what these were. And so we took the spectra of these objects, of these quasars, and they didn't really help either, because optical spectra showed really weird emission lines. So I put here in these colored lines where H alpha, H beta were hydrogen, the Balmer series of hydrogen B, as well as doubly ionized oxygen, this dark green line. And nothing's matching up with them. And that was really weird. We didn't know what to think. This is the spectrum of 3C273. We'll follow that quasar through. Nothing was really matching here. We didn't know what these lines were until Martin Schmidt in 1964 pointed out they could be redshifted. And this is H alpha. Here's oxygen. Here's hydrogen, hydrogen, hydrogen. This gives it a redshift of about 3/4, which tells us that 3C273 is about 2.5 billion light years away, which at that distance gives it a luminosity of around 500 times that of the Milky Way. Here's a nice, beautiful Hubble image. On the left is what we saw before, where it just looks like a star. But now we've developed techniques to where we can block out that inner part, and we can actually see the underlying disk. And it's several orders of magnitudes fainter than the bulge. About 1 in a million galaxies host these luminous quasars. About 5% of galaxies host those bright, Seifert-like bulges where we could see the disk relatively easily. And about 30% of galaxies host some low-level activity. Now, what is causing all this? I imagine many of you already know the answer because I'm using the word quasar. When we look at quasars over time, we see that they actually vary in brightness quite a bit, but very random. Here's Once again, 3C273, a century's worth of data, which is very impressive. And you can see it varies like on the timelines of hours. Stellar populations can't do this. Stars do not do this. Huge groups of stars, I mean, cannot do this. And we've got to remember sort of a little bit of our relativity. We got to remember causality. If an object changes brightness, its size must be smaller than its light travel time. So to understand how variations in luminosity give us clues about an object's size, let's imagine that you are a master of the universe and you want to signal to one of your fellow masters 1 billion light years away. An active galactic nucleus, that's what these are called, these active galaxies, would make an excellent signal beacon because it is so bright. However, suppose the smallest active galactic nucleus you could find was 1 light year across. So each time you flashed it on, the photons from the front end would reach your fellow master a full year before the photons from the back end. And if you flash it on and off more than once a year, your signal would be smeared out. Similarly, if you use a source that was 1 light day across, you could transmit signals that could flash on and off no more than once a day. And using this logic and the fact that the luminosities of active galactic nuclei sometimes double in a matter of hours, we can conclude that their light sources must be less than a few light hours across. In other words, the incredible luminosities of these active galactic nuclei and quasars are being generated in the volume of space no bigger than our solar system. So for 3C273, with its hour-long variability, it has a size of less than about 6 AU. That is about the size of the solar system out to Jupiter's orbit. And we can actually calculate the mass 3C273 would have to have for it to not be blown apart by the sheer amount of light it is producing. And that gives us a lower limit of about 300 million solar masses. Yes, 300 million solar masses. Now, just out of curiosity, let's calculate the size of the black hole at that mass. Remember, Schwarzschild radius, 2 times a constant times the mass divided by the speed of light squared. And when we do that, we get a size of about 6 astronomical units. Sounds like a black hole to me. This is the only known way to account for these extreme luminosities of these quasars, of these Seyfert galaxies, is that the central object is a supermassive black hole surrounded by a swirling accretion disk of very hot gas. The gravitational potential energy of matter falling in towards the center of the black hole is converted to kinetic energy, and collisions between infalling particles convert that kinetic energy into thermal energy. That resulting heat causes this matter to emit intense radiation that we observe. And this will generate incredible amounts of energy. The most energy efficient black holes can release about 40% of its mass energy. So 40% of 300 million solar masses is a lot of energy. And this also accounts for this very small size. We are pretty dang sure that, especially thanks to the pictures from the Event Horizon Telescope, we're pretty dang sure that most galaxies have a supermassive black hole at the center of them. And whether or not a galaxy is a quasar or just a normal, quote unquote, normal, just ordinary galaxy, depends on, is the black hole doing accretion at that point? If it's not, then it will appear like a normal galaxy. If it is, then it will be looking like a quasar or a Seyfert galaxy. And we've noticed several weird relations between black hole and other properties of the galaxy. So for example, the mass of the black hole is strongly tied to the mass of the bulge. And here by bulge, I mean either just the central bulge of a spiral galaxy, what is colored in red here, or just the entire elliptical galaxy, which is just a bulge. So here on the vertical, you can see the black hole mass. On the horizontal, you can see the bulge mass. You see it's a pretty tight straight line. Yeah, there's some scatter, but it's a pretty tight straight line. Furthermore, the black hole masses are generally between 1/10 to 1% of the bulge mass. So on the vertical here is percentages of the ratio of black hole mass to bulge mass. And then on the horizontal is the bulge mass. You see it's almost a flat line, it's a horizontal line. There's some scatter between 1/10 and 1%. What's odd is that the black hole mass is not at all coupled to the disk mass. Disks are just there for the ride. So once again, on the vertical is the black hole mass. On the horizontal is technically the disk brightness, but it correlates roughly with mass. And so there's no light here. It's just kind of a cluster of points. For whatever reason, the black hole only cares about the bulge. The disk is just there for the ride. It's not doing much. And what we've noticed, because we're talking about galaxy evolution, let's return now. Stop talking about black holes and let's return now to galaxy evolution, is that we've noticed that those active galaxies have these huge jets coming out from the bulges. We don't know how these jets are created. We don't know how many jets are created. That's still an active area of research. You can see Hercules A, that galaxy at the center, invisible, and then its jets are in radio, that nice red on the outskirts. Possible impacts from this, these very, very strong outflows could stop accretion onto the black hole, shutting it down. Maybe this is the end of an active galactic, active galaxy. Maybe these strong outflows actually push the gas out of the galaxy, shutting down star formation in a process known as galaxy quenching. We're just not sure. This, I could keep saying this is all very, very active research. And so in recent years, we have put together all of this into one big picture of galaxy evolution. And it's sort of, it's very complex. Galaxies are very complex systems. Here, we've got on the left versus right. Left is internal stuff, right is external stuff. Top versus bottom. Top is fast, things that happen on a fast time scale. Bottom is things that happen on a slow time scale. So stuff that happens relatively fast and internally is protogalactic gas cloud collapse. Maybe that forms galaxies. Stuff that happens relatively fast but external, galaxy mergers, ram pressure stripping, things that happen in clusters. Internal secular evolution, stuff that just, the galaxy is doing on its own. Maybe it's forming spiral arms. Maybe it has an active black hole. Maybe it's having these huge galactic winds. External secular evolution. Maybe gas is infalling from the nearby universe. Maybe there's going through some minor mergers like the Milky Way is going. Maybe it's swallowing up a dwarf galaxy. Maybe there's some galaxy harassment. No mergers, but just, two galaxies kind of orbiting near each other and tugging on each other a bit. And in all of these cases, star formation, gas recycling, metal enrichment is happening in all of these cases. So it's a very, very complex thing. And only in recent years have we really paid attention to the role of the secular evolution, the slow evolution stuff, the spiral structure, the gas involved, galactic winds, minor mergers, that kind of stuff. Only in recent years have we really begun paying attention to that and seeing how much more important that is to galaxies than mergers and gas cloud collapse. So it's still, I can keep saying, a very active area of research. Thankfully it is, otherwise I would not have a job. This is exactly the stuff that I research. Definitely, we talked about a lot of different things tonight. Please, please, please comment down below, direct message me, whatever you prefer, and ask questions. I would be more than happy to answer them. This is exactly in my wheelhouse, so to speak. So next week we will talk we'll start talking really about cosmology and talk about the birth of the universe. And then the following week we'll talk about the death of the universe. So quick jaunt into cosmology. As always, let me know if you have any questions. Like, comment, subscribe, all that fun stuff. And I will see you all next week.